Fortunately, there are really good methods that are both powerful and that have led to the detections of hundreds to thousands of planets. One of the ways that we can detect planets is essentially via the Doppler effect, essentially looking at the spectrum of the star. So we cannot really do observations or getting spectra of planets and looking at what's happening to them, but we can actually track the star. And we've seen that stars contain lots of absorption lines of essentially all the elements. What we can try to do is to monitor the star, actually look at all these absorption lines, match them up with the values of the lab, and actually trace a common redshifts and blue shifts that is periodic. If we do that, and if we measure lots of lines, we can get enough precision to calculate what is the average velocity induced on the star because a planet, for example, is orbiting it. And this will allow us to essentially solve for the mass of the planet, because we've seen in section 8, we can calculate the mass of the star. Through Doppler effect, we can calculate the velocity of the star. We can also use the period and Kepler's laws to infer the average velocity of the planet, and therefore we can solve for the mass of the planet. This is, of course, still challenging. The sun's motion due to Jupiter is still just about 13 meters per second, and therefore you still need to have big precision, even for Jupiter-like planets. So this is obviously even more challenging for lower masses. And all you have to do really is to use the Doppler effect, which we've covered before, and remembering that in astronomy, we typically use this eye angle away from face on, and in most cases, these velocities, the velocities that we measure, that the star is essentially moving towards us and then away from us in a periodic way, will be affected by this sign I term, and therefore the mass of the planet, as we'll see, is typically affected by this term as well, unless we have a way to determine the inclination of the orbit of the planet. In order to understand how this is done in practice, I just generated this example. Let's just look at one specific line. And as we shall see, this is a really massive planet that is so massive that it's almost like a brown dwarf, but just go along with it so that you can understand the concept. Let's say that we're monitoring a specific star and we're taking spectra of the star and measuring H beta. And we're measuring the observed H beta location, essentially as a function of time, of days since the first observation. We know what H beta should be like in the lab, that's lambda 0, and we then take measurements with proper error bars that we estimate from our uncertainty in spectra. And we realize that this goes up, so H beta is redshifted, and then it goes back to rest frame as it gets bluer and bluer shifted. It gets to a lower value, and then it comes back up again, and this is repeated with a constant period of something like almost 4 days, 3 point something days. The important thing to realize is that by taking data like this, we can actually determine the period. So you can calculate as the time it takes for this line to go down to bottom, or we can actually calculate it from peak to peak, or just from the position repeating itself anywhere within the data. And the other thing that we need in order to use the Doppler effect is to calculate delta lambda, which is the difference between rest frame and any of the peaks. Delta lambda is not the full amplitude from minimum to max. It is the amplitude or the difference between rest frame and one of the peaks, either maximum or minimum. Provided you understand this, then you have all you need to actually apply the radial velocities to detect and study extrasolar planets. Let's be even more specific and realize that the star that we're monitoring is an A-class star with a solar mass of 1.8 solar masses that shows its regular shifts in the H beta line. If we have access to this data, it means we can actually determine the average distance of the planet to the star, and by using the Doppler effect and measuring delta lambda, we'll be able to infer the mass of the planet. In this case, by using this graph and measuring the time that it takes for the graph to repeat itself, we can calculate that the period is 3.5 days, and also that delta lambda is 0.01 Armstrong. Now, by using Kepler's third law, and remember this is written in the general form, we can actually find that the average separation between the planet and the star is actually 0.055 AU. You can calculate it first in meters, and then you can transform it in AU. And remember that you don't need to memorize any of the constants. You can just look them up in worksheets or in the lecture notes. The next step that you can take is to understand that the average velocity of the planet is just square root of g mass of the star over the average separation. You can actually calculate this because we've now calculated the average separation from Kepler's third law, which involved us calculating the period. So this is where the period really comes in. By using Doppler effect and the delta lambda we measured, we can actually see that the average velocity observed, and this is important, is around 5.96 times 10 to the 2 meters per second. And this means that the velocity of the star, the actual velocity or the average velocity of the star, is given by the observed one divided by sine I. And we're going to keep this sine I because we don't really know how inclined the orbit of the planet really is. Finally, because we know from center of mass considerations that the velocity of the planet times the mass of the planet is equal to the velocity of the star times the mass of the star, with these velocities being the average velocities, we can finally solve for the mass of the planet very simply from what we've gathered from the Doppler effect. And this will lead to an answer that is 1.25 times 10 to the 28 kilogram. And this is divided by sine I, again, to do with our uncertainty or our ignorance to do with inclination, at least for now. And we can also convert this to the mass of Jupiter. If we divide this by the mass of Jupiter in kilograms, this will give us 6.6 over sine I of the mass of Jupiter. We could therefore conclude that we're looking at a planet that's even more massive, 6, almost 7 times more massive than Jupiter. Radial velocities are currently one of the most successful methods. The success was really boosted by an instrument that is called HARPS that sits on this telescope in Lucia, and that allows you essentially to track stars night after night, to take spectra of stars, measure their absorption features, actually combine them all to get down to velocities of something like 3.5 kilometers an hour. That is an extraordinary precision. That's achieved because you are combining essentially all absorption lines in the spectrum of the star in a spectrograph that is incredibly stable. Now things got even better with espresso on the VLT that is now working, and that essentially using the same technique. This was built by the same team, so they used all the knowledge, but they got it even better. And on a larger telescope, this allows you to get down to precision of something like 0.3 kilometers per hour. This is just really, really, really impressive. I mean, we're talking about 300 meters per hour. Radial velocities are incredible to detect mass, and with increasing precision, we can now detect some of the lowest planets that are really like Earth around sun-like stars. However, there are still limitations to radial velocities, and for example, the fact that there is really no information about the size. We can only really determine the mass. And without a size, and only with the mass, we have no idea what the planet is actually made of. And for that, we actually need to use another method, which we'll cover next.